Let's explore heaps, a fundamental data structure used in priority queues and efficient sorting. This is a max heap, a complete binary tree where each parent is greater than or equal to its children. A heap is a special complete binary tree with a specific ordering property. A heap is a complete binary tree, meaning all levels are filled except possibly the last, which fills from left to right. In a max heap, every parent node has a value greater than or equal to its children. In a minute heap, every parent node has a value less than or equal to its children. Here we see both types. The max heap has 50 at the root with smaller children, while the min heap has 20 at the root with larger children. Heaps are incredibly useful for managing prioritized data. Priority queues use heaps to ensure the highest priority item is always accessible in constant time. Computer systems use heaps to schedule jobs, executing high-priority tasks before lower-priority ones. In a priority queue, items with higher priority are served first, regardless of when they arrived. Let's see how to insert a new element into a heap. First, we add the new element at the bottom level, in the leftmost available position, to maintain completeness. Then we compare the new element with its parent. If it violates the heap property, we swap them. We keep swapping upward until the heap property is restored throughout the tree. Here we insert 85. It starts at the bottom, then bubbles up because it's larger than its parent 70. Removing elements from a heap requires maintaining the heap structure. In a heap, we always remove the root element, which is either the maximum or minimum depending on heap type. We then take the last element from the bottom level and place it at the root to maintain completeness. Then we compare this new root with its children and swap with the larger child if needed. We continue this downheap process until the element finds its correct position. After removing the root, we place the last element at the top. Then it sinks down to restore the heap property. We can efficiently build a heap from an unsorted list using the downheap method. First, arrange all elements into a complete binary tree structure, filling from top to bottom and left to right. Then, apply the downheap operation to each parent node, starting from the bottom and working up to the root. By working backwards, we ensure each subtree becomes a valid heap before processing its parent. Starting with arrays 7, 5, 8, 9, 4, 6, we arrange it as a complete tree, then apply downheap operations. Heap sort uses a heap to sort data efficiently in place. First, we build a max heap from the unsorted data using the downheap construction method. Then, we repeatedly remove the root, which is the maximum element, and place it at the end of the array. After each extraction, we restore the heap property by downheap, working with a smaller heap each time. We continue this process until all elements are sorted in ascending order. Heap sort repeatedly extracts the maximum element and places it at the end, resulting in a sorted array. Let's review the key concepts about heaps. Heaps maintain a complete binary tree structure where parents are always greater than or less than their children. Upheap moves elements upward to restore heap property after insertion, while downheap moves them downward after removal. Heaps provide efficient implementations for priority queues with constant time access to the maximum or minimum element. Heap sort achieves efficient O of n log n sorting by building a heap and repeatedly extracting elements.